好，我们接下来看。So let's move on to the per unit inductance of cylindrical structure, coaxial cylindrical structure. So we do this according to the Ampere-Circuitial law that is governing the relationship between magnetic field intensity with the current source. So actually we should begin with this equation, okay? The equation on the Circuitial law on the bottom right corner. And firstly, we can get rid of the second term because we are talking about static current, statistic current, 静电流而已, static current only. So we don't have to worry about the time derivative of electrical flux density. So in this equation, you see the closed loop integral of magnetic field intensity equals to the amount of current encircled by this closed path. So suppose we draw a random closed loop like this, and we have currents emanating from the surface encircled by this yellow loop. Then the total, not the total magnetic, not the magnetic field, not the magnetic field intensity directly, but the magnetic field intensity H times this path times the length of this path. The closed loop integral of H equals to the total current passing through this yellow area. So if the loop is not random, is kind of a symmetrical like a circle, then the closed loop integral of H, so suppose we have a circle over here. So the distance from the radius of the circle is R, okay? And then the closed loop integral of this path, of this circular path is what? 2 pi R times H. H is in the direction of phi direction, okay? So suppose the z-axis is this way and currents flowing in the z direction. The H field is in the direction of phi direction. So 2 pi R H phi equals to the total current encircled by this closed loop. And in this case, is the total current I flowing on the inner cylinders. Okay? So you can put a subscript IA, well, anyway, IA equals to the minus of IB, right? Okay. But anyway, so let's, according to the textbook, just put I over here. Then, the magnetic field intensity can be found by simply put I over 2 pi R for this relatively simple geometry. So the magnetic field intensity within this coaxial area is the same or not? Not the same. It's not homogeneous. It's a function of R, right? It's a function of R, but it's actually proportional to the inverse of R, right? So the closer, it's valid between A and B. So the smallest value, the largest value is actually I over 2 pi A. And the smallest value is I over 2 pi B. Okay? Now, you must have a problem, or must have a question. All right, you can understand that the currents on the inner cylinder build up the electrical field in its neighborhood. But we also have currents on the outside, right? Will they produce magnetic field? Well, yes, thank you. They do produce magnetic field. But if you think of this problem as a whole, the total effect of the currents as crosses, or buzzes, if you are Japanese, right? Of those crosses cancel each other. Okay. There's a rumor that I bet you must have already seen a bunch of Lao Gao and Xiao Mo, right? They say that the moon is an observation device drawn by the alien to the neighborhood of Earth. So it's a hollow structure, which means it has a very stiff steel-made or iron-made shell on the outside, and it's empty on the inside. Okay, so what happens if you get into the moon? Okay, you mean get into the inside of the moon? What happens about the gravity of moon? You know that on the outside of the moon, the magnitude of gravity is about 1/6 on the Earth. So if moon is hollow and you get into it, you will feel no gravity. The gravity within the supposedly hollow moon is 0. Of course, if you think the gravity from individual part of the moon is still there, but the overall effect onto you cancels each other. And this is about the same story for this case. Now, of course, the cross currents, the current flowing into the opposite direction, still produce magnetic field, but their overall effect is canceled in this case, so you don't have to worry about this. Okay, you only account the magnetic field produced by the currents within your imaginary path. Okay. So do you aware that we don't have to have a real current loop, real loop around the inner cylinder? We just have a imaginary loop, imaginary path, and we can calculate the magnetic field intensity with this assumption. Okay. All right, so here's the expression for magnetic field intensity. Here's the expression for magnetic flux density. Just times the permeability within the space. And you know the expression is only valid between R smaller than B and greater than A. And the total flux, which is the surface integral of B in this cross-section area, can be found by taking the surface integral. Surface integral. Well, surface integral is supposed to be Wait a minute. Wait a minute. Okay. The surface integral is taking on which places? It's not the circular region between outer and inner cylinders. Okay, not this region, because the direction of this surface is what? In the z direction. So the surface integral taken here is on this region. Okay, it's in the phi region, in the phi direction, and it's a strip, long strip extending in the z direction. Okay, so you're taking the surface integral of B passing these blue strips. So the integral is written as B, the dot product of B with dr for r equals to A to B. Okay, so here is the total magnetic flux passing through this blue strips on the blackboard is mu times I divided by 2 pi times log of B over A. Okay. Okay, you put B and A as the limit of this integral region. So you have the total magnetic flux. Then, according to the definition of inductance, which is the ratio of magnetic flux over electrical currents, you can have the per unit length inductance of this coaxial structure is written as phi over I, so it's mu over 2 pi times log of B over A. Okay? And this is the total inductance. And here is the per unit length inductance. So you divide the total inductance over length. Okay, so to get the per unit length inductance. Note that in the textbook, the per unit length inductance, per unit length capacitance, and per unit length conductance is written as calligraphic type. 它的字体是那个花体字啦，就是那个英文里头英文的缩写一样，有所谓的书法体calligraphic，应该是叫 calligraphic 吧，好吧，我不是很确定这回事，但是它是所谓的花体字啦，所以你看到花体字的话，就是单位长度的那个特性，所以这边的 L、C 还有 G， 它把它写成花体字，代表是 per unit length 的电容值、电感值跟电导值。Okay, so we have found all the 3 properties: the unit length capacitance, unit length conductance, and unit length inductance. So let's examine the 3 parameters at the same time. And you found they are in a very similar expression. They are all related to the geometry, that is log of B over A. They are all related to material property, which are epsilon, sigma, and mu, respectively. So if you do this, you take the product of L with C, the product of inductance and capacitance. You end up with mu times epsilon. Does that ring any bell? Mu times epsilon. mu times epsilon is what? Is the inverse of the speed of light, of the square of speed of light. 这个好了，那个英文字母跟那个拉丁字母不够用啊。这边 c 指的是光速啊。Speed of light equals to what? Square root of mu times epsilon. 好 ，1 over square root of mu times epsilon. What is the purpose of this section? Well, it's kind of lay out the foundation for transmission line theory. So in the next 2 months, we will learn the basic for transmission line circuit. Transmission line circuit, which is also referred as circuit, is not as the conventional circuit theory. Okay? The circuits you learn from your 电路学1, 电路学2 is the so-called lump circuit, 对 lump circuit, or quasi-static circuit, or quasi-static approximated circuit. In the analysis of lump circuit, in the analysis of lump circuit, the signals arrives to any place in the circuit instantly. 所以你在传统电路学分析的时候，我这边开关一打开，你那个电压讯号直接就过去了。你没有所谓 propagation delay 传播延迟的观念，在电路学、传统电路学里头，我们没有讨论 propagation delay。什么叫 propagation delay？propagation delay 就是我在电磁学1的时候讲的你看到的我不是现在的我，对不对？你看到的我是几个或几十个 nanosecond 之前的我，一个 nanosecond 光速跑多远？30公分啊，对不对？光速一个 nanosecond 跑30公分，所以看看你跟我隔多远吧。假如你跟我隔3公尺的话，你看到的就是10个 nanosecond 之前的我。所以我们在传输线理论的课程内容的时候，最主要的区别就是讯号我们还是讨论电压电流讯号，但是这个电压电流讯号要从传输线电路上面的左边跑到右边都要花时间，它要从右边再跑回左边也要花时间，所以主要的区别就是我们要把 propagation delay 的这个观念带进来 ，OK？ 那这个等效电路的等效 CGL 等效电感、等效电容、等效电导，它是让我们的电磁现象给你这个电磁现象一个接近传统电路学的一个观念，类比于传统电路学的观念，让你比较好入门，好入门。所以我们的传输线理论，你看起来还是会用电路学的一些语汇，但是你自己要铭记在心的就是，在传输线理论里头，讯号的那个时间传播的延迟是重要的，它会影响到整个传输线电路的分析。所以第5章里头其实就是把第5章其实是在铺梗把传输线电路相关的一些特性跟各位做介绍。然后第6章的话，我们会用 time domain 的方式来去检视传输线的特性，传输线电路的特性。从 time domain 下手比较容易了解到底传输线上发生了什么事情。不过第7章我们会改用 frequency domain 的角度来去看传输线 电路理论，因为在微波电路的设计跟微波电路元件的应用上面，我们基本上看的都是 frequency domain 的 response，frequency domain 的特性。所以从应用来讲，那个 frequency domain 比较好用，比较重要啊。所以我们第7章还是要教各位一些传输线设计上面的基本工具。但第6章我们是先了解嘛传输线，所以我们会从 time domain analysis 来入手啊。那 Chapter 5呢，就是做一个铺梗啦，就是做一个基本的工具的介绍。所以这是为什么我们这边才会去做这个单位长度电感电容的推导啊。它其实跟你要建构传输线电路的元件特性是有关系的。好，那这边我们看到的就是一个单位长度电感电容电导之间的一个重要的关系。So as you can see here, the product of per unit length capacitance and per unit length inductance is invariant to the geometry of the transmission line, right? You don't see any geometric parameter D or W or A or B. Nope, it's just related to the material composition of this structure. For this case, you look into the product of per unit length capacitance and per unit length inductance. So it's equals to the product of mu and epsilon, the product of permeability and permittivity. And the other case is if you take the ratio of G over C, unit length conductance over unit length capacitance, the geometric relationship goes away as well. You end up with sigma over epsilon. The ratio is invariant to the geometric parameters. It's only related to the material property. It's the ratio of conductance over permittivity. So the consequence of these two relationships is important, which means you don't need to derive per unit length conductance and per unit length capacitance and per unit length inductance for every structure you have. You only need to derive one property. For example, you only need to derive the per unit length capacitance. Then the per unit length conductance and per unit length inductance can be found using this relationship. Okay? So you don't have to find all the 3 parameters. You only find one parameter and you can get the other 2 with the relationship. Only one of the 3 parameters is independent. So with the other 2 obtainable from it, and you can, as long as you know the material composition, as long as you have the material properties. All of this result is deduced here for the coaxial cylindrical arrangement. It's a general result valid for all arrangements involving 2 infinitely long parallel perfect conductors embedded in a homogeneous medium. So we just look into the coaxial cable case. So the coaxial cable is used by the cable TV, the setup TV box. What other transmission line structures you can think of in your household? Telephone lines. Do you have telephone lines in your home? I guess half of you may say no. Okay. Well, okay. If you ask this question in China, I would say 99% of the households do not have lead lines. 室内电话我们称为 landlines 哈 ，landline 是室内电话。那在台湾的话，毕竟我们有一个几十年的世代都是用室内电话的啦，哈，所以应该蛮多的家庭了哈。假如你的至少那个 homeowner 假如是在40-50岁以上的话，像我这样的话，我们家就有 landline 哈 ，OK。Landline is made of what? It's just 2 wires. It's just 2 wires, but it's still in the form of transmission line. Well, what signal goes on the telephone lines? Unmodulated acoustic wave signal. So the transmission medium we have for landlines is practically the same as the telephone lines 140 or 130 years ago. It's basically the same, just 2 wires. So what you need is a microphone and a speaker. The microphone turns acoustic wave into currents and voltages, into electrical signal. Then this electrical signal, which is not modulated, goes directly into the telephone lines to reach the other end. And at the other hand, you use a speaker to convert voltage signal in electrical signal into vibration of acoustic wave, so that you can hear what is said on the other hand of the telephone. So this mechanism is practically the same. And the best thing about it is it can be interrupted very easily. You can hear what your neighbor says if you devise something that we will describe in the next few slides. Okay, so it's relatively easy to break into a landline. Okay, but it's somewhat more reliable because the structure is relatively simple. One example is if you have a large earthquake and most of the power lines goes off, the telephone landline may still usable as long as the operating office is operable. OK 所以只要那个收发机的那个基站那边还能动的话，基本上没有电你的电话也能通啦。只要你用的是比较传统的电话，只要你用的是那个什么 Panasonic 无线电话的话，那也不能通了。因为后面那一段它还是有 modulation。所以好了，我要讲的事情是假如虽然那个电话线的那个线路很原始但它还是传输线。所以早期的那个中华电信在提供家用宽频的服务，它的那个宽频的讯号其实也是走在电话线上的，只是说那个是 modulated，所以它可以跑的速库就有什么56K，假如你有听那个什么高候选人的那个我是没听啊，我听说什么他小时候3岁就在那边听哔哔哔的那个 modem 的那个声音了。我记得我第一次听到那个声音的时候是高中还是大一的时候吧。OK， 你要在那边叽个大概1-2分钟才会连上网络然后它可以撑到多少？1个 M 2个 M 大概到20-30个 M 吧。OK 假如状况好的话 ，OK， 所以即便是那么简单的 pair wire， 我们叫 pair wire 2条线，那透过 modulation scheme， 它其实也可以给你还可以的讯号传输量了。那当然了，在4G、5G 的时代，那个讯号的输布无线的输布又超过那个电话线了。怎么超过？ 用更厉害的那个 modulation scheme 啊，更厉害的调变技术啊。好 ，Alright, so any two infinitely long parallel perfect conductor can be used to form the so-called transmission line. So, for example, we have parallel plate. 平板结构 parallel plate, and we have looked into coaxial structures. So here are in this table 5.2 in your textbook, list the per unit length capacitance, conductance, and inductance for several kinds of transmission line structure, right? So parallel plate is the first one, coaxial, second one. The third one is parallel cylindrical wires. That's the two-wire structure. As you can see, they are all related to epsilon, sigma, and mu. And on the other hand, they are also function of geometric parameter. For example, for pair wire, the per unit length capacitance is pi epsilon over arc hypercosine of D over A. So you learn how to find arc hypercosine using your calculator. Okay, you can bring your calculator to the exam, but not with your phone. Okay, I will allow scientific calculator to be used in the exam. Yeah. So you must learn how to find it. Find the arc hypercosine of this thing. And that's the third one is pair wire. The fourth one is this. What is this? This is a coaxial cable get kicked. 被踢了一脚的 coaxial cable， 所以它的那个 center conductor 歪掉了。所以歪掉了之后，它的单位长度的特性就会被影响到。所以假如是标准的同轴结构的话，它的几何结构就是 AB 嘛。大家这边被踢了一脚，所以中心线偏了一个 D， 所以那个 D 就跑到那个式子里头。OK So this table is convenient to give you the so-called 送分题啊。对啊，看表按计算机这个会吧？OK 但不会太多分啊，最多个5分10分的OK 但是要会按了，好不好？And the fifth one is this one. So this is, you can think of this as pair wire shielded with a metallic enclosure. So it's a protected transmission line. So it's more difficult to break into this kind of transmission line because the outer conducting layer provide certain degree of protection to this kind of transmission line. And the third column, the third row here is the per unit length parameter with this shielded parallel cylindrical wires. Alright, and here are some illustrations for coaxial cable, pair wires. 你没有看过这个？这我打赌应该你们看不到，我小时候有看过。这个东西是什么？这个东西是那个古早时代电视机的后边的那个接到天线的那个传输线。它是黄色的，那宽度大概1公分左右。是哪种电视？不是那个接 AV 端子的电视，不是是那个有一个像柜子一样，然后前面有一个木头拉门的那个抽屉的那种电视，知道我在讲什么吗？你阿嬷家的那个有丢掉了吗？不要丢啊，对不对？ 拿去卖给怀旧餐厅，可能可以卖个几万块。OK， 然后小时候那个就不见了。OK， 真可惜。好，这个还不到古董啊，这个叫做 vintage vintage 的那个 stuff， 它是300欧姆的那300欧姆的传输线刚好可以接一些像是亚基乌达巴木天线那种东西。那还有像这种这个是我们刚刚说有保护的嘛？这个是转的。我们之后会讲原因它转它也有保护的效果让讯号比较不会漏掉那右下角的话，我们称之为导波管有方的叫 rectangular waveguide 圆的叫 cylindrical waveguide， 它们通常是用在军事设备上，因为它们要 handle 高能量。其他的那个传输线，假如你跑的那个讯号是几瓦 ，OK 啦，几百瓦，几千瓦，几万瓦大概就会烧掉了，几千瓦或几万瓦就会烧掉。右边那个的话，它的耗损很小，因为是全金属的嘛，所以耗损也不过是变成热而已，顶多是那根管子修腾腾啊那样。所以它的耗损比较小，然后也比较能够散热，所以基本上那种100万瓦等级的那个雷达系统天线就是用这种传输线的。好 ，All right, so let's move on to example 5.7. It's in this example we're looking into the per unit length per meter of parallel wire structure and looking into the field and the potential distribution and variation within this structure. So we were looking into, we will try to find out one of the 3 transmission line parameters, capacitance, conductance, and inductance. You just need to find out one of them. So let's find out the capacitance for this case. Suppose we have electrical charge, static electrical charge, displays on these 2 wires, and they displays on these 2 wires homogeneously. So they have the same amount of charge. Okay, so you have 2 wires. And you place positive charge over here and negative charge over here. And the total amount of charge on the 2 wires are the same. Okay, first question. If you are the positive charge on the right hand and on the left hand side, would you distribute it like this? Would the positive charge on the left hand side distributed homogeneously or uniformly on this cross-section area, providing that there are negative charge on the right hand side? All right, so now we have 2 parallel infinite wires, and we have a static charge on the wires. And as I already explained, the charge density is somewhat different on the cross-section of the 2 wires. Okay, so more charge can be found in these 2 neighborhoods because the attraction between positive and negative charge. And we would like to find the capacitance of this structure. Okay, so what are we going to do is find the capacitance. Not that the wire has certain radius. The radius of the wire is what? A, okay? A is the radius of the 2 wire, and And D is the distance from the center of the wire to the middle between the two wires. Okay, so let's look into the, sorry, no geometry. Okay, so here is only the geometry, okay. So D is the distance between the center and the middle of the two wires. And here is another parameter B. B is what? B is the distance from the middle of the two wires to the position of highest voltage, over here, okay? So which means, well, the geometric center of the wire is this point. However, the highest voltage in this structure is this point. They are not found at the same point. Why? Because the currents are not distributed evenly across this cross-sectional area. So the highest voltage location move to the right for this case and move to the left in the right hand side, okay? But you can find the equal potential circles, inside and outside of the two wires, okay? Now, so let's first consider this just one infinitely long straight line charge of uniform density, which is rho sub L0. It's located along the z-axis to simplify the geometry. This symmetrical geometry is associated with the problem indicates the potential is dependent on the cylindrical coordinate r. So with just one wire, with just one kind of charge, the voltage potential, the electrical potential built up by this line charge can be found using, it's a one-dimensional problem, okay? It's a symmetric on the, it's invariant to the z-axis. It's a symmetric, which is also invariant to the phi axis variation. So the only variable pertinent to this problem is r. Okay, so we only care about the variation in r. So the Laplacian of a cylindrical coordinate system for this problem is this. Okay, you see we only have r coordinate involved in this Laplacian. The complete Laplacian of v also includes z and phi, but because of the problem geometry, it's invariant to z and phi. So we only have r. So the general solution for this second order differential equation is v equals to a times log of r plus b. So this is the general solution. How do we find out the value for a and b? Well, of course, we need to find out the appropriate boundary condition for this problem. As we have talked before in the last week, we said that in cylindrical coordinate system, you cannot put the zero voltage reference in the infinity. Otherwise, you will, because the voltage and because the voltage is related to the log of r, natural log of r. So you may have a problem by setting r equals to infinity. It's not defined. It's not defined. So anyway, let's say the zero voltage reference is located at R sub 0, okay? It can be anywhere, all right? But we'll just refer it as R sub 0. Then the voltage difference between your observation point, which has R, will be A times log of R minus A times log of R sub 0. And you can simplify like this. So here is the expression for your electrical potential V. However, we still don't know the value of A. But we can find out the electrical field intensity expression by taking the gradient of V as this. The gradient of V equals to minus of A over R, and the direction of the electrical field is into the R direction. So as you can see here, you will have electrical field going out symmetrically on these cylindrical surfaces. So next, you can apply this relationship, the integral form of Gauss's law of electrical field, by taking the surface integral of E and equals to the amount of charge on the right-hand side, which can be found by what? By charge density rho times the distance, times the length. Rho times L equals to E times 2 times the cylindrical surface area. So you can end up with A. That will be the solution of A. So next thing, you can put A back to the expression for voltage and electrical field intensity as well. And now you can verify that the gradient of V equals to minus of E, like this. Okay, we'll continue next week.